So I can't see how many people are here, but I'm going to optimistically assume there are people here that are very attentive. So thank you for coming. And the topic today is the background work subsystem in Realm. And so I'm going to bounce through a bunch of code and stuff, but I want to start by trying to set the explain what the problem is that we're trying to solve in the first place. And so, in general, Realm is very asynchronous runtime. And so there's lots of things going on all the time. Many of the things are application tasks, in which case we provision a thread per Realm processor, and it's pretty clear, basically the Realm task schedulers for each processor are in control of deciding, okay, well, what should that one thread per processor be doing at any given time? But then there's an awful lot of stuff in Realm that is asynchronous to the application tasks and needs to run on different threads. And those things include things like doing copies, for example. They include doing dependent partitioning operations. They include handling network messages, both the handling the incoming messages, but also making sure to tend the network interfaces and get all the outbound stuff queued up and submitted at the right times. It includes things like asynchronous file I/O in some cases. It includes, what else am I forgetting? Polling for CUDA events is another thing that happens on background threads. So there's all sorts of stuff that we do asynchronous to the application, and they need to be on thread somewhere. And in the early days of Realm, basically what the way the Realm internals were structured is each of these things had its own thread. And they part of the reason for the thread reservation system was trying to figure out how many of these threads there are and assign them to groups of cores so all these asynchronous things would not interfere with application threads. The trouble is they still interfered with each other a lot, and the issue is we've got I think if you were to go through the different kinds of background work things, there's on the order of a dozen plus categories, let alone multiple DMA. There's many now for DMA, for example, but there's tons and tons of them. And so there's and the trouble with them is any given one is not usually active all the time. We'll get to one important exception a little bit later. And so you're stuck with this problem of, well, if each one is its own thread, do you give each one its own core, in which case some of the cores go underutilized, or do you assume that on average, only some fraction of them are, busy at a given time and provision fewer cores and munge them all together onto those fewer cores? And if you do it as a bunch of separate kernel threads sharing a smaller number of cores, then basically you're asking the OS scheduler to take care of deciding which one gets to run at a given time. And this is problematic because of a couple things. First of all, we have some things that are higher priority than others, and we want to make sure that the high priority things get constant attention. But the other thing is quite often these asynchronous work items are interacting on shared data structures and taking mutexes and stuff, and we really, really don't want anything to be context switched out by the OS while the while mutexes are held, because then the guy that swaps back in isn't going to really make any useful progress either, and the system gets very stuttery. So after struggling with this for quite a while, we switched over to this new model of background work, background workers and background work items. And basically the idea here is to take the scheduling out of the OS's hands and put it back in Realm's hand. So instead of each kind of asynchronous work being its own thread that the OS scheduler schedules, now each kind of asynchronous work is captured in what's called a background work item, and there's a fixed number of background work threads that schedule, that Realm schedules background work items onto in order to in order to get that work done. And so rather than having a bunch of threads specific to each item, you have a smaller set of common threads, and they collectively work on all the background work items. And now, once you do this, you can start deciding, for example, to pin the background work threads, which you don't do by default, but you can. But it also it gives us better visibility of when we're oversubscribed on background work items and the like as well. And so it's an ongoing theme in Realm has been that it turns out OSs aren't quite built for the sorts of things that Legion and Realm want to do, and it's often easier just to take, to do it yourself than to try to argue with Linux until it schedules things the way you want. So I'll go into the code in a moment, but at a high level, basically everything in Realm that used to be an asynchronous thread, pretty much, is now a background work item. And I'll describe the interface for how you become a background work item and how you advertise work and get your work done. And then we have a background work manager that manages a pool of threads that they go and do that work. And let's see, we'll probably get to it today. There's two kinds of background work threads. There are dedicated threads. So when you do -ll-bg work on the command line, you're telling Realm how many dedicated background work threads to provision. But the other thing that there's support for, although I believe it is currently disabled by default, is it's possible for any arbitrary other thread in the system to basically volunteer to help out with background work. The idea behind this was that if you had other threads that were hard provisioned, like say the thread that runs the utility processor, then you would have a way for when it recognized it was idle, then it could jump over and help do background work and basically help with throughput when it's otherwise idle. And like I said, that's disabled by default because it turns out it brings back a lot of the same problems as before, which is, okay, well, if you're going to go do some background work, how do you come back in time and be responsive to new tasks that get pushed into your task queue? And it turns out that's hard. The default there is that it's off, but there are hooks for it, and we'll see some of them as we go through. The other high-level concept that becomes important when you're looking at taking what was done by an OS scheduler and moving it into the Realm background work system is some sort of notion of preemptive multitasking. Some background, some background work items are very short and latency sensitive, like, please pull the network once. And some can be quite long, like, please do this enormous dependent partitioning operation. And if if you're completely greedy about getting work done, then you can have trouble that when you have the bursts where, maybe there's 6 background work items that want attention and only 4 background work threads. Then if you take each work item and run it to completion until that work item is completely idle, then you may have a responsiveness problem for the other ones. And so on the flip side, we're not going to do preemptive multitasking because A, that's hard to do at user level, and B, I just told you before, we don't actually want to do that. We certainly don't want to be preempting while people are holding mutexes and stuff. And so to kind of split the difference, the background work system in Realm has effectively a cooperative multitasking approach where you set time slices, and background work items are encouraged to get as much work done as they can, but also pay attention to the time slice. And if it's expired, then yield up the thread in case there's other work items that are also demanding attention. So hopefully that's a good high-level description. Any high-level concept questions about that before I start jumping into some code? Okay. So I'm going to start out as always, we're in runtime/realm. And I'm going to start with bgwork.h and bgwork.cc, which is the core of the background work system. And so I'm in the header file right now, and I'm going to work backwards. I'm going to start with the work item and then talk about the threads and the managers. And so down here at the bottom is a background work item, basically abstract parent class. So if you have some sort of work that in the Realm internals that needs to be done in the background, you will inherit from this background work item class. And you pick up basically just a couple key pieces of functionality. First of all, everyone has a name so that when we print stuff out, you have some idea which work item is chewing up all your cycles. I'll talk about the background work manager next, but any given work item needs to be registered with a manager, basically which manager is going to be responsible for actually servicing the work requests. And the key real method, and again, this is a pure virtual method here because this is an abstract parent class, is this do work method. And so the manager will be responsible for periodically calling do work on a work item, as long as that work item is active. And each time it is called, we're given this time limit, this work until argument, which basically describes how long your time slice is. So rather than giving absolute time, it's abstracted into this object, and basically, as you'll see, the time limit object has a is it done yet type API. And so I'll show a couple examples of various specializations of this, but this is where the key unit of work is done. And then the last piece that's important is how you actually how you actually get attention from the manager, and that's this method called make active. And so a background work item, when it has work to do, it should call make active, and that will schedule it with the work manager. And there's an important invariant here, which is that you can't make active more than once. And this is a performance optimization, but also a source of fragility. So it's one I've actually been on the fence about whether it should be quite so, whether the last little bit of optimization is important. But you'll see a couple quirks right now with the way make active works, that you need to basically, effectively every call to make active will result in exactly one call to do work at some point. If you don't do all the work, then there's ways to make yourself active again. But you need to be very careful that if you have work queued up and you call make active and you haven't had your do work yet called, then you're not supposed to call make active a second time. That can confuse things. And right now it's the responsibility of each background work item to maintain that invariant itself, that it never calls make active more than once. In debug mode, we actually have some tracking code in here that makes sure that that doesn't happen. That basically if something is in the active state and you call make active, it'll flag it as an error. The extra Boolean required to track this state, and importantly the atomics that are associated with it are actually, the Boolean is not a big deal. It's the fact that you need atomic operations in order to manage this that has me shying away from doing it in optimized builds. But if you've got weirdness with a background work item that you think might look like race conditions and stuff, then turning on debug realm and making sure these things aren't firing is a good way to do that. But yeah, so the first order, it's very nondescript. You register with the manager. I'll talk a little bit about the NUMA domain stuff, although it's only partially supported or partially implemented right now. Strictly speaking, it's implemented. It's just not actually really utilized right now. And then do work and make active are the main two methods that you mess with in your specialization. Okay, so that's the work item. I think I'm going to go kind of breadth first here, and then in the second pass, I'll show some specializations of work item. So the other main class in this in bgwork.h is the background work manager. And so this is the thing collecting my thoughts. The background work item is coded to support the notion of there being multiple managers in a system. In practice, there is exactly one manager that the realm runtime starts up. And so you can think of it that way for now. If we needed different background workers, different managers, in different, sub-processes in the future, you might see multiple managers. But right now, there's one manager that does everything. And so it has a bunch of configuration options. You can configure the number of generic workers. So this is LLBG work. You can spin up per NUMA workers, and a per NUMA worker will only take work items that are also associated with that same NUMA domain. You can also decide whether you want to pin those threads, and then stack size and some scheduling stuff, basically spin interval and time slice for deciding how workers try to find work before they go to sleep. And so you can, part of the step is reading all these command line parameters, configuring it, and then there's a couple methods that are invoked by the main runtime startup to basically spin up dedicated workers and tear them down again. And then there is, I'll get to the actual scheduling in a little bit, but then there's this worker class, which is basically if you want to do background work, if you want to help with background work, then you implement this worker class. And so, like I said, there's a dedicated worker thread class that implements this, but it's also possible for other threads to temporarily become a worker. And if you want to temporarily become a worker, you just create one of these objects, you set the manager, you specify your max time slice and whether you're specific to a new domain, and then you can call in to do work. And this is a way of saying, hey, I would like to do work for up to this amount of time. And then you will temporarily be co-opted by the work manager, and it will call do work on various work items up until this time slice is satisfied. There is a second argument here, which I don't think we actually use right now, but it's wired in, is that in addition to the time limit being a fixed time slice, there's also a notion of being able to say that I can also have an interrupt flag, which immediately terminates the time slice kind of out of band. And so if you call into a non-null pointer here, then setting this atomic bool to true will cause the very next call to has this time slice expired to immediately say yes. And so if you wanted a way to break in a little bit sooner, then you could do that. And I believe the utilities processors may do this. The trouble is it's still, because the work items are still cooperative, right? They're not going to be able to stop mid-work. And so interrupting is not really a true interrupt. It's more of a, at your next convenient stopping point, please hop out. So it's not quite as valuable as you'd like. The core of the work manager, since it's got lots of, so super multi-threaded thing, right? We've got a bunch of workers, either dedicated ones or temporary ones, and work items are often marked active by other workers or task threads. And so this is designed to be a completely lock-free setup, and basically it uses a big old bit mask of work items that, each work item is assigned an entry in the bit mask, and, sets its location to 1 when it has work to do. And then when a worker tries to claim an item, it goes in and basically tries to atomically clear a bit. If it clears a bit, then it's claimed that work item and goes and does work for it. And then and so that's the high level, and so it's based on atomic, test and sets and test and clears in order to advertise work and to claim work. And then there's a little bit more machinery that's responsible for allowing workers to go to sleep if it turns out that the workers are actually underutilized. And so there are mutexes here, but they just control. The mutex just controls actually assigning new work items to slots, so it's not used in during the main execution of things. And then there's one other mutex. It's a funny mutex that's used for putting things to sleep. And so I can't remember if I've actually really gone through mutexes in one of these discussions, but mutex is what you think of as a normal mutex. This delegating mutex is a special kind of mutex. Let's see if I can find where I put it here. That instead of lock and unlock, it has attempt enter and attempt exit. And the deal here is that if a lock is held by one thread, then another thread that attempts to enter it fails the attempt but does not retry it. Instead, it increments a counter that the current owner of the lock will see when they attempt to exit, and they will not be allowed to exit until they did the work that was delegated to them by the thread that failed to enter the lock. And so it's I don't know where this counts in. I think this is technically lock free because you never spin on a lock. Instead, but you can, if you're the holder of a lock, you can be forced to do somebody else's work because they didn't hang around to do it. And so it basically amounts to a counter, and when you enter the lock, you snapshot the current counter, and when you try to leave, you atomically try to clear your bit without on the assumption the counter hasn't changed. If the counter has changed, it's because somebody else failed to acquire, and now you need to make sure that whatever work they were responsible for is done as well. There's no actual indication of what the work is that needs to be done, and so you use this only in cases where there's some other state that you've already updated that indicates what work to be done. So for example, if you set a bit in the in one of the bit masks, then you might attempt enter in order to try to wake up a thread. And if you fail to attempt enter, well, then somebody else is currently waking up threads, and they'll see that you want a thread woken up as well and can do it for you. So that's the funny mutex that makes it still mostly block free. And I think that's the data structure at a high level. I can go into some of the code, but I want to stop again and make sure people have a chance to ask questions about this now second tier of description.
So how do you keep priority on the work items in the bit mask? Like, presumably there's a queue of some kind that keeps them in order of what order they're supposed to try to run, at least, even though it's lock free.
Yeah, so I sort of lied. There isn't actually any priority right now. Okay. But the way we do priority is basically just have 2 levels or 3 levels of bit masks. And you have the high priority ring and the low priority ring. Okay. Each ring is currently round robin. And so there's no starvation within a ring. But yeah, there's no priority mechanism right now. The places where we do have priority happen within given work items. So the network module can do priorities within its work item, and similarly the DMA system can do priorities within its work item. But there are no priorities between work items right now.
Yeah. Right, because there could be like a work item like that hasn't gotten any active running time yet that's still sitting in the queue, right? That the network module can't see yet, right?
But the work item is the network module. It's not an individual packet.
Oh, I see. Okay.
Right. So yeah, there's a 2-tier approach here where the work items are not individual.
Yeah, you got your
do this depth part operation. They're whole subsystems.
Okay. So these aren't like the DMA transfer requests and stuff.
That's right.
Okay.
That's right.
All right.
And that's a good question, because otherwise the bitmask thing clearly wouldn't work, because there can be literally millions of actual pending asynchronous operations.
Okay.
But they don't show up as individual things here.
Right. So the background work items are like realm submodules and stuff that are effectively the things that need running time.
That's right. And so when we talked about DMA stuff like a month and a half ago now, each channel is its own background work item, for example. Well, strictly speaking, each transfer descriptor queue was its own background work item, right? So, but those queues were one-to-one with channel today. So basically, each channel has one work item, which is, do I have any work, for CUDA mem copy, for example?
Right.
And there's 2 reasons for doing this. One is hierarchy is good, and it keeps us from seeing a million different asynchronous things here. But the other reason is it also allows for a subsystem to easily provide mutual exclusion on stuff within its own subsystem. All right, so if I have 27 things that all want to do HDF5 transfers, turns out I can't actually have multiple threads do that concurrently anyway. libHDF5 doesn't allow it. And so by going through an HDF5 channel background work item, and basically it can be the thing that makes sure it has mutual exclusion on the various kinds of HDF5 work that need to go on. Yeah. And there's 2 reasons for that mutual exclusion. One is, right, if the underlying library requires it. The other is that, it can just make the execution fundamentally more efficient if you aren't trying to moderate multi-threaded access to the transfer descriptor queue, for example.
Right.
And so I'll give a couple examples later. There's patterns where so by default, because of the make active thing and the one-to-one relationship between make active and calls to do work, that you actually know that the do work method on a work item is actually thread safe, or is thread serialized, if you will, by default. The only way it fails to become thread serialized is if you were to call make active while you were still inside of do work. And if you choose not to do that, right, then you can treat that entire method as thread serialized and get rid of a bunch of locks and stuff. If you want to allow multiple pieces of the same kind of work to be done concurrently, then you're allowed to call make active in the middle of your do work method. And if you do that, you just need to know that there are now maybe 2 threads in the call to do work at the same time.
Mm-hmm.
Okay.
Another question is, like, do you have any mechanism to detect if one of the background work items like vastly overruns the suggested time limit?
Yes. sort of. I think there's logging. I don't know if it's actually active. And part of it is that some of the background work items aren't very good at paying attention to that right now. And so it's not really a false positive. It's actually, a violation of the time slicing. It's just that not all the work items are great at handling time slices right now.
Which ones are the main offenders?
Big, horrible dependent partitioning operations are going to be the big winner. Okay. I don't think we stop mid dep part operation right now.
Yeah.
The copy system is much better about breaking things up into smaller pieces. And we talked a little bit about that last time.
Yeah, I'm thinking like if like it ran over by like a factor of 10, like maybe issue a warning or something. But yeah, I guess if
and like I said, I think there's a hook. Let's go find it. I know the log message is in here somewhere, but I'm guessing it's not enabled. Yeah. So okay. Yeah. It looks like you have to actually turn it on to turn on the profiling.
Okay.
And so if you do that, then it will complain about overshoot. And it looks like there's also no margin here. Any overshoot is immediately complained about, which is almost certainly too chatty.
Yeah, that's probably too much. I give it a factor of 10, but yeah.
Yeah. So the other thing that I intended, and I haven't never got around to actually implementing, but would be goodness, is the intent was also to gather statistics over time, both in terms of how active overall was a given work item, what was the average activity of the average number of active work items at any given point. How does that compare to the number of actual workers you had, and then some notion of how much time did work items spend idle, waiting for a worker to attend to them. And the thinking was that could be used to allow people to have a somewhat more principled way of deciding when to dial up or down the number of background workers that they give to Realm. In terms of one thing it'd be nice, for example, and we talked about trying to do this in Legion Prop, haven't done it yet. It'd be nice to see the background worker load.
Yes.
As a thing in the Legion profile, in particular, if you see things, where you see things running slow and you see the load pegged at 100%, right? That's an indication that maybe you got a hot spot there.
I'd even take NVTX annotations for now, but yeah.
Right. Well, so we talked a little bit, not in this setting, but there's a realm level profiling thing that has been on the back burner for quite a while now that's very similar to NVTX and generates Insight style pictures of things, and that is how I look at when somebody complains that Realm is being slow at something, right? It is that I look at to see what the what the load on the various different workers is, and so yeah, we definitely should find a way to expose that. The one challenge is that it is, very verbose, right? Yeah. We're time slicing a lot of stuff onto threads, and it's hard to decide, whether the information is useful or just, burying you under lots and lots of pointless data.
Yeah.
But that's the challenge by any low level profiling tool. Okay. Any other questions at this level?
I asked one last one, a stupid one.
Yeah.
The utility processors are their own threads, right? They're not handled by the background worker threads.
That's correct. All Realm processors have their own threads.
Good.
That are not part of background work. Like I said, they're allowed to temporarily be a background worker if they want. But it turns out that, like I said, when we turned that on, we found that we lost performance because we were not being responsive enough to latency sensitive meta tasks.
Yep.
And so I believe we turned it off by default again.
I think that was the right answer. Yeah. Okay. I'm done.
Okay. So I wanted to give a couple examples of actual background work items. And so here's one. This is right when you trigger a Realm event that can make a bunch of things that were waiting for that event become active or enqueued or ready in various ways. And it's quite possible to get patterns where one Realm event has hundreds or thousands of directly or transitively dependent tasks or other operations, and we've seen cases where the poor thread that is the one that actually triggers the event then sits around waiting, in some case milliseconds, to just enqueue thousands of tasks and copies and other stuff in various places, and so since that puts load in a place where the user wasn't expecting load, it can cause performance issues. And so what Realm does is Realm keeps a backlog of events that need to be triggered, and it's willing to trigger a couple kind of in line at the place where a thread says, hey, this event is done. But it turns out there's tons and tons and tons of things that need to be notified. Then they get queued up, and it's the responsibility of the event trigger notifier to trigger the rest, to signal the rest of the waiters asynchronously. And so again, right, this inherits from background work item, and therefore needs to override the do work method. And so if we go over here to we give ourselves a useful name, and then this trigger event waiters is basically this isn't directly part of the do work of the background work thing, but this is basically the interface into this thing. If you want to trigger events in Realm, you hand a list of event waiters to this thing, and you give it a time limit, how long you're willing to wait until you'd really like to get onto whatever you're doing in your own thread. And this is important both if we're doing this inside of a background work item, because quite often it's background work item, background work that enables other background work. But it's also useful, if you're in a task thread. We set this to some modest number, I think like 10 microseconds, to say basically don't spend more than 10 microseconds in my thread doing this. If it's more than that, then offload it somewhere else. But basically what this code is doing, it's doing two things, but the one that's relevant here is it's going to walk this list basically in this loop here and try to trigger events, normal events or poisoned events, as the case may be. If you get lucky and exhaust the whole list, then great, we just return without doing anything. Otherwise, we stop this loop once this time slice is triggered until time slice is expired. If it's expired, then we check to see if we have any other triggers we didn't get to yet, and if so, we put them into these delayed queues. There's a delayed queue for normal event triggers and a delayed queue for poison event triggers. And so this is a common pattern you'll see in background work items, that basically we take a lock. Before we enqueue this stuff, we check to see whether the queues are currently empty. And the reason, and then we enqueue this stuff. And the reason we did that first is that if we were empty before, and now they're not empty, now we know we want to, we need attention that we hadn't asked for before. And so we're going to call make active here. Whereas if we're adding to queues that are already not empty, then we'd already called make active once, and we're not supposed to call it again. So like I said, there's a really common pattern of before you enqueue, you check to see if are you transitioning from idle to not idle, and if so, that's when we go ahead and call make active. We call make active outside the lock, importantly, though, because contention is bad. Okay, so that's basically this entry point. The end result is we trigger some things, and other ones go on the list. And then here in the do work method, we basically, again, we're going to give it a time slice how long we can run until, and so we come in, we grab the lists of work to do, and actually kind of the same loop as above. As long as the work until isn't expired, we go ahead and trigger stuff, and then once it's expired, we go ahead and we put anything that's left back on the queue. And the catch here is, so this pattern of grab the list at the front and then operating this list meant we weren't holding the lock while we were popping events. And so it also keeps from the creeping problem of people constantly adding to the list while you're trying to drain the list and you never stopping your time slice. So the idea is we only trigger things that were already on the queue before do work was called. But if any are left, we need to make sure they're merged back in with anything that was added since then. The last thing to note here is that do work actually returns a Boolean. And so instead of at the end here where we go add stuff back, we actually there's another reason why we don't requeue the work here I should talk about in a moment. But we do the same thing, right? When we add whatever events we didn't trigger back to the list, we check to see if we were empty. If we went from idle, if we went from empty back to full, then we want to make sure we re-enqueue ourselves. Instead of calling make active, though, we actually just return true or false from the call to do work. So basically, returning true from do work is just like calling make active right at the end of do work. Except that it results in slightly faster scheduling in the background work manager if there aren't very many work items active. Basically, if you return true, then the thread that was working on your work item may immediately just call back in without having to go through the higher level rescheduling thing, right? If we know that basically there are no idle are no pending work items other than this one that is just now made active again, we can just immediately go back in. And so the cost of having the time slice trigger when the system is relatively idle is super small, because we just come out and I said, I can step right back in again. There is a little gotcha here, though, which comes from multi-threadedness, which is that by taking things off this, by swapping out these lists and making the lists empty, then it could be that some other thread that's calling this method here, triggering other things, may get to the point where it wants to enqueue stuff, and it will see that the list was empty when it queued, and so it may call make active, right? And so that's the reason why we can't call make active down here unconditionally if we had work left, because it may be that make active had already actually been called while we were running. It also means it's possible for there to be multiple threads in this do work function at the same time, right? You can have one thread doing the do work from the first time, and it may work out that while we were doing that triggering, some other thread enqueued some event waiters to be notified, and then a second background work thread took that item and started running do work for that as well, which is the other reason why we don't try to do anything beyond the ones that we saw when we started, which is that there can be some other thread that's already taking care of those. But again, you get to manage how thread serialized it is. And so in this case, we serialize just the beginning and the end. We don't have to do any locking in between because we carve off what we have. There's other cases where a concurrent pusher of work isn't allowed to actually call make active while we're popping, and that way we know that the only time that you'll have perfect thread safety or thread serialization within the do work method. And that's how the CUDA one works. And so I was going to go show that one real quick, unless people had questions about this one. Am I going too fast or too slow?
I think it's just fine.
So that was a question. You're saying it's okay?
I'm saying it's okay for me, at least.
Well, you're by no means the middle of the distribution. Okay. Well, let me keep going, and folks can ask questions. And as always, if folks want to ask questions after the fact, as you digest things, then that's fine too. I'm now in the CUDA module, and there's a GPU worker in the CUDA module, which is the thing responsible for tracking all the work that's been launched to the GPU and noticing when it's done. There are some vestigial things in a lot of these things where they do still have support for their own dedicated background threads. I didn't delete that stuff when we switched to the background workers, but these are all disabled by default. So you can turn them on in weird cases, but in most cases, we use the background work system, and you definitely shouldn't have any of these things using both their own dedicated thread and also the background work system. So we can ignore the start and shut down background thread and look at add stream. So for example, here is so when you put work onto a GPU stream, the model in the CUDA subsystem is that you add work to the stream, you add some sort of event notifier or something, and then you tell the GPU worker that, hey, there's work in this stream, I'd like to know when it's done. And what that will do is that will add, we'll go into the GPU worker, we've got a list of active streams. And the same kind of pattern you see, right? We take a lock because we're going to mess with this active streams. I guess it's a vector. But before we push onto it, we check to see if it was empty. And if it was, then, and we're using the background work system, then we're going to call make active. And actually, so maybe this isn't the right example because this one does do the requeuing pattern that I was talking about. So, okay, well, this isn't the example I wanted. But so now in do work, right, we have that list of active streams. And so this is another pattern that shows up. It's not, like I said, it's not the one I thought I was showing, but it's a useful pattern. So we pop something off the front of the list, and we also immediately check to see whether there's any other active streams on the list. If so, we could do it ourselves here, but if there's other background work threads that are available, then those threads could do it too. So what we'll do actually is we will immediately, if the list is empty, we'll immediately call make active, which means other threads can come in and call do work and pick off other things on the list. It does mean we need to be careful that the stream that we popped is not on that list. Otherwise, we'll have two things trying to pop from the same stream at once. But so once we get past this point, right, we no longer have kind of safe access to the popping side of the queue. But since we removed the stream from the queue, we do still have dedicated serialized access to that stream. So we don't need to take as many locks in here as we try to reap events and issue copies, although we don't really issue copies anymore because of the new DMA system. Mostly what we're doing here is we're reaping events. And then the same pattern, right, that we reap events, making sure that we tell it how long we're willing to wait. And so you'll kind of see the work until thing gets nested through all the background work stuff, at least in places where it's been plumbed. And then the same pattern, right, that if we fall out because we ran out of work, then we want to requeue the stream. And to do that, we take the lock, and again, same pattern where we check to see if it's empty, and then we push, and then we return true if it was empty, which means we need to requeue. And this pattern here, we do need to call, right? We do need to return true even if somebody else queued before, because if they queued before and it got drained, then we need to make sure we queue again. And so basically, you know, the invariant here is that if it was empty at the time you added, if you were the thread that made the queue go from empty to non-empty, then you're the one who needs to make sure that make active is called either directly or via the true return value from this method. Pausing for a moment for you to ask questions, and also for me to see if I can remember a case that has the other pattern. Maybe it's in the GasNet code. Yeah, it's a level. I'm trying to figure out why my screen is being weird. Okay, well, I'm not going to try to do it live, but there, I will after this meeting, I'll go find the background work item that I'm trying to think of, where we basically keep track of effectively consider ourselves still to be non-empty as long as we're in the do work method. And it's only at the very end of do work method that we check to see if there's other work, and if so, then return true. And the idea there is just to make sure that the do work method itself is thread serialized and therefore a lot easier to write. Okay, so we got about 10, 15 minutes left. I don't think there's a huge advantage in going through. Well, let me do a super quick skim of what the scheduling loop looks like. As I said, basically so this is the worker do work method, right? So this is the one that implemented by the background work manager that is responsible for calling through to the do work on actual work items that need it. And so at a high level, basically, right, we come in with a time slice given to us from outside. And so we turn that into an absolute time where we want to stop. And then we go through a loop where we, okay, so the first, a bunch of nuances here. The first one is that it is possible for work items to be created after the worker threads have started. And so you need to know how many, how many slots in the bitmask to check. And it's not just any one is worth checking because of the NUMA domain stuff, you actually need to know whether a given work slot is one that you want. And so the first check we do is basically see have any new work items shown up since we last did this. If so, we're going to actually, maybe this is just the wraparound check for the round robin. Yeah, this is just round robin. There's another one where if a new work item comes along, we need to check it to see if it's one that we want to be paying attention to. But this is just a round robin, right? If we've gotten past all the work items on one pass, we're going to come around and start with slot 0 and try again. Because the number of bitmask bits, I think, is up 256 or 1,000 or something, well more than one UID64. And so we need to do it in chunks of 64 bits that we can do atomically. So we figure out which one we're at, and then we basically, let's see. Okay, so here's the one where we detect new work items, new kinds of work items. And so we, if there are bits in the active mask that we've never seen before, well, then we need to figure out who they are and decide whether we care. And so we do that. We ask, we need to take a ref count on the work item for race condition fun. But then once we've got it, then we can ask, is it compatible? Does it, ideally a work item is supposed to say what is, how responsive is it to checking that things are expired? And if it says that its min time slice is longer than this work thread is willing to give, then it will be disallowed. Similarly, if it's in a different NUMA domain, then it'll be disallowed. But once it does that, then basically we build this allowed work item mask per worker. And we only build it when a work item first shows up, so we don't have to keep testing it every single time we go through the list. But then once we've got that allowed list, we can then use that to mask the active mask and basically say, what are the bits in this mask that I actually care about? And as long as it's non-zero, well, then there's a bit we're going to go to try to claim. And so the standard test and set game of basically figure out which bit we're going to grab and then try to clear it in the active work item mask. And if we successfully clear it from 1 to 0, then we are we've claimed that piece of work. And so that's what's going on here. And in here, so once we've claimed it, now this is basically figure out how long we're going to give that do work method to run. And then we call do work here. Right, so this is calling the work on it with that time limit that we computed right there. And as I said, do work is allowed to return true or false. If it returns true, then there's the fast mode where it turns out that there are no other work items that need to be serviced, in which case we're just going to loop around this loop and just call right back into do work again. If there are other work items, then we need to be round robin, and so we just mark this one active and expect some other thread to get to it, and we'll continue with the next thing in our round robin list. And that's basically the schedule loop. It's meant to be super lock free, and generally in profiling it seems to be pretty fast, so I'm pretty happy with it. But I haven't, I bet actually there's probably a few cycles here and there to squeeze out if somebody were super motivated. I think the, at least the profiles I've looked at so far, the background work system is not usually, there's burstiness that kind of no amount of threads can help, but for the most part, it's generally not the bottleneck in most of the things we look at. I think that's mostly what I wanted to cover today. We can stop a few minutes early but first we'll take any questions that anybody has at this point.
So this is unrelated to what you were talking about, but are the active message polling threads part of the background work system, or are they their own standalone threads?
Yes, no, that's a good question. They are part of it, and that was I was going to go back to here. So GasNet EX polar. So the polar and GasNet EX is absolutely a background work item. And actually, so this was a good example. Thanks for reminding me of this one. So the polar is a funny one in that it's basically effectively always active, right? When we tell GasNet, okay, it's time to start polling, it immediately says, hey, I'm active. I want attention. And that puts it on the list, and eventually one work item will get to it. And if we go look at the do work method, we're going to restrict the time limit like any other work item should. But if there's a bunch of different paths through this based on time slots and stuff. But the important thing about this is every single path through here always, well, okay, there's one exception. Almost always return true. The only case where we don't return true from do work on the polar is in the case where we're shutting down. In every other case, basically, the minute the polar is done polling, it immediately says, hey, I would like to do more polling. And so what this often means is that if you look at a profile, you'll see that one background worker thread is just constantly polling.
Yep.
Right. And this is actually partially why initially I didn't have this idea of returning true. I just said, oh, you can just call make active yourself. And the trouble is that actually led to a performance problem with the polar in that the polling responsibility kept hopping from one thread to another with some overhead each time you did that. And so by returning true here, it basically means any case where the background work system is not oversubscribed, the polar will sit on one thread. Basically constantly. But the instant there's enough other work to do, then it'll follow the round robin rules and give other things a turn. And so this kind of fits the model of, if there's a thread idle, then we constantly poll, which gives us the best possible response time to incoming network messages. But if there's other stuff to do, well, then we start slicing our time between them. And yes, that means we're less responsive to the network, but we had a bunch of other stuff to do. So there's a good chance we're not actually as sensitive to the network as we might be in an otherwise idle case. There is a little bit of a challenge that I know Hassan has been seeing with the UCX module, which is that in some cases he'd like to actually he has a bunch of different. He doesn't have one polar. He can have up to in some cases one and maybe in the future even two polars per GPU. And you don't really want all of them to all be occupying a thread nonstop. And so there's some challenges there. But in the case of GasNet, where it's only useful to have one thread polling at a time because you poll on behalf of every endpoint, then this works well. Basically, you just keep returning true, and as long as there's nothing else to do, then we keep polling. And if there's something else to do, well, then we share.
Okay, so effectively, in the latency case, you've always got one thread that's always polling, but if there's lots of messages coming in, it's possible for multiple background worker threads to be handling them simultaneously. One will grab some, the next one will grab some. Yeah.
Yeah. So okay. For the polling, there's always only one thread doing it. Now the catch is when we call a GasNet poll here.
Right.
If they're incoming messages, that will call a GasNet receive handler.
Right.
Okay. And I can sort of show that here. It's a little bit off topic, but it's probably worth looking at here. Handle short. Okay. So this is the method that gets called if a short active message shows up while we're inside that GasNet poll call. And it decodes it enough to figure out what kind of message it is, and then it's going to hand it to the incoming message manager, which is part of the active message system.
Right.
And importantly, it also passes the whatever time slice we're operating on. We're still inside of polling, but thanks to GasNet, we have to tunnel the time limit through a thread local variable. But if we're inside the polling thing, we forward our time limit until on to add incoming message, which allows the message manager to decide, hey, do I want to handle this message right now, or do I need to queue it up myself?
Yeah.
Right. And so for messages that are willing to be handled immediately and for time slices that aren't expired, it may handle it immediately. And if it doesn't, then it turns out the incoming message manager is also a background work item.
Right.
and it will queue up the pending message in its own as its own background work item rather than
Yeah.
since it's off the network at that point. It's just inside the message manager.
Right.
And so there are absolutely cases where one do work method just causes transitively causes some other method, other work items do work method to be called later because there wasn't time to do it in line.
So you just suck all the messages off the wire and then stick them in the queue and handle them later in some other
That's right.
background work.
That's right. And then I guess the other point with GasNet, for the AM poll method. Oh, that's not what I wanted at all. Where was I? Control F doesn't do what I want. Yeah. Right. So one property of GasNet is that once you call AM poll, once you call into this, there's no way to tell GasNet about time slices. I'd love to be passing the work until variable to this, but GasNet doesn't support that. And so this is one case where if there's a lot of messages coming in, it may be that we have trouble breaking out of this loop. And that can be a challenge if you have a small number of background work items and background work threads and a whole bunch of other unrelated background work to do.
I feel like we hit that case sometimes.
I've not seen it so much in profiles, but that's the sort of thing that, having that logging at the background work scheduler system to complain, that, certain work items are way overrunning their time slices would be useful.
Yep. And does the ECX backend have the same problem, or is it just GasNet that suffers from that because it sort of forces you to handle all the active messages?
It actually has the opposite problem. It has an upper bound on how many things it'll handle, and at least from the experiments Hassan was telling me about a couple weeks ago, it sets it too low.
So he doesn't pull enough off the wire, and then the network backs up. Yeah,
exactly. So scheduling is hard. Ideally there would be. Ideally, we'd use that interrupt flag approach I showed you before. That in theory, we could call into something with a relatively generous work slice, but the background work scheduler. So let me jump back there real quick. So when we build the time slice for calling do work here, we pass the interrupt flag if it came from outside. But if we're running a dedicated worker, this interrupt flag is never set. In theory, what we could do is we could actually use the interrupt flag even for the dedicated workers. And when we make a work item active that oversubscribes the number of workers that are available, we could go set the interrupt flag on all the all currently active work items in an attempt to shake them loose a little bit sooner.
Yep.
There's a challenge there because you don't necessarily you want to do some amount of work each time, right? For example, we went to the memcopy system and just did a single memcopy each time and then said the time slice expired. We spend a lot of our time thinking and not a lot of time memcopying. So you don't necessarily want to, zero out the time slices either. And that's why it's a little bit tricky to figure out. Speaking of time slices, we are done with the hour though.
We are. Does anybody else have questions before we wrap up for the day?
Okay, well, let's wrap up then. And if anyone has questions asynchronously, then call make active, and I will service your request once I hear about it.
Okay, great. Thanks, Sean. See everybody